So I'm going to be telling you about Iron, which is a web framework for Rust. And the big thing about Iron is that it's meant to be kind of fast, concurrent, all the things that Rust is good for. And although it's not very good at kind of distributed stuff, it does basically everything else at the moment. So the reasons we'd want to use Rust, compete with C, run on embedded devices, which is very useful. I've used Iron on a Raspberry Pi before, and it runs great. You get Rust's nice type system, and you also get the great package management and community. So Cargo is pretty good, and being able to manage all your stuff with Cargo instead of like Git submodules or some insane thing is quite nice. So as I said, Iron is this framework for building web apps, and it's built on top of the Hyper HTTP library, which was written by someone at Mozilla and is used by Servo as well. So it's quite a mature HTTP library underneath. And then what Iron gives you is the sort of like structure for building easy kind of apps. And one caveat is that it's blocking I/O. So Rust doesn't have a very good sort of story around non-blocking HTTP yet, but Metal I/O is in the works, and it's doing like ePOL KQ stuff with raw TCP at the moment. And I think people are planning to build full-on like HTTP implementations on top of that. But that's just to be clear that that's not really what we're talking about today. We're talking about blocking I/O and threading via like a thread pool. Okay, so this is the structure of Iron. Basically, it's modeled after Express.js, if anyone knows that. But you take a request in, you chuck it through all these various filters, which really at the core are just this handler object. And then you spit out a response. And how we implement this in Rust is we have traits for each of these things. So the main handler trait says that a handler is anything that's send, sync, and any. So they're just, I'll talk about them in a sec. But basically you just have to define one function called handle, which takes a version of your handler object by immutable reference and a mutable request, and spits out a response. And the response here gets wrapped in an Iron result, which is really just a little type alias for a result and an error that's specific to Iron. So the idea is that you propagate your request through here, and if something goes wrong, you spit out an error variant of this thing, and it'll like send a 404 or a 500 or whatever you want it to send. And then one of the other traits, the around middleware takes a handler and kind of wraps it up and gives you a new handler. So it's a way of doing things like response timing, for example. So with an around middleware, you could take in your request, time when it gets there, call your main handler, and then on the way back out, work out how long it spent in there, and then log that somewhere. So you could say like that request took whatever. Yep. Yeah, so you could, is it the same ability for the before and afters? Yeah, it's exactly the same. So you could implement your request timer as a before and an after, or as one around. So yeah, it just depends how you wanted to structure that. And before and afters can do things like authentication, and the idea is that you build up a whole lot of layers of different handlers and things. And then you have some sort of core, which is usually, in Iron's case, a router. So far, these are some of the things that Iron can do. And it does all of these things via a sort of plug-in system. So Iron's core doesn't do much on its own, but it allows you to define these 4 things. And then all of these are implemented in terms of those. So routing, for example, basically just says, give me a whole bunch of like URL patterns and handlers for each one, and I'll make a big handler that handles the routing, basically. There's logging, there's database interaction. At the moment, Postgres seems to be the best one that's best supported, but you could write a fairly simple wrapper for the MySQL Rust driver. We can do JSON, we can do HTML templating, and persistent storage, which allows you to share a bit of data between threads. Because by default, Iron will spin up a whole thread pool, and as requests come in, it'll handle them on a different thread. But if you want to share something between them, you've got to use like a mutex and all this stuff, and the persistent storage will handle that for you. Okay, so here's some code to do some JSON stuff. And I think this is probably some of the best JSON handling I've seen in any language, because it's nothing specific to Iron, but the Rust compiler can automatically generate serialization code and deserialization code, for custom structs. So if you just make a struct like this, you say, I've got a name that's a string, an ID that's an int, and a whole list of somethings. I don't know, I just making stuff up here. But to serialize that into a JSON string, all you have to do then is call JSON encode on one of these things, and it will give you that string straight up. You don't have to write anything. You don't have to say that this field maps to one of these. Like you can if you want, but by default, if you're just dealing with very simple data, or you just want to not think about serialization code, the compiler will do it all for you. And there's another serialization library that can also do this, but it relies on nightly, and it's called SERD, or like SERDay or something, serialization, deserialization. But it won't be stable until compiler plugins are stabilized. So for now, the inbuilt compiler encodable, decodable traits are pretty good and easily usable on stable. And then here you can see that you can use closures as handlers. So this handler is just a closure that takes one of these request objects and gives back a result with a response in it. And the response here, typically you can kind of do it in this nice declarative style where you just say, I want a response with this thing. So in this case, because we're just giving it a string, it knows to set that string as the body. But you can also feed in tuples here. You can put like a status code and a body, or like some headers and a body and a status code, or all sorts of things. And that's basically the structure of it. And yeah, that's the JSON you get back from serializing one of these automatically. Okay, does anyone have any questions about the sort of model or how that works or anything? Yeah, sure.
Not sure if you'll cover this later on, but how does that actually respond to a particular route that's given?
Oh, okay, yeah. So in this case, this one will just respond to every HTTP request that you send in. And I haven't actually, I don't think I include an example of routing, but I probably should have. I'll spin something up and show you what the routing looks like. In fact, I can do that now. Let's see, Iron router. Yeah, why not, right? Like we've got time. Not that. This one. Okay, so there's actually a macro for routing, which is quite nice. Okay, so you can do it like this, where you just say, I want to route get on route to a certain handler, or this query to a certain handler. That will extract the whatever you put there as well, whatever the string is. So if you did like /name, it would give you a little variable down the way. Yeah, a lot of unwraps there, but that's how it works. You do proper error handling if you're doing it well. Let's just see. I'll just show you the macro quickly, because the macro looks cool, I think. So that's the macro. You can say like, get this, do this, get that, do this, post this, do that, which is pretty nice. And that's just implemented, I'm pretty sure, as a normal, yeah, it's a macro rules macro. There it is. Although the body's not shown, probably because it's horrendous, but it's probably not. Reem writes pretty great stuff, so. I could click source, but I'm not going to. Yes.
So you mentioned, sorry.
Yep. Okay. So you mentioned MIO as part of the async story for async IO. It's been a while since I've looked, but I know there was some talk about doing async IO in the standard library. Do you have any sense of what the future of that is?
I haven't followed it really closely, but as far as I'm aware, I think async IO in the standard library is pretty much dead. I don't know. Don't quote me on that.
That makes me sad.
But there will be, I think the plan is to have like a blessed async IO implementation, which will probably be Mio at this stage. I don't know. I'm really just speculating. I feel bad that I'm on video saying things that are possibly wrong. That's okay. Cool. Okay, so another thing you want to do when you're writing a web app is handle query parameters. And here we have something, a name set to blind example and an age set to 9,000. And there's, of course, a plugin for Iron that handles this. I'm using the word plugin here in the technical sense because Iron has a thing called a plugin that it uses. So we'll see how that works in a minute. But basically you can say, I got my request object. You can do this kind of getRef method on it. And you pass in not a string or what you want to get, but actually a type. So this thing, by giving it the URL encoded query type in there, returns a hash map. Like Rust knows that returns a hash map. And you're thinking, how the heck does this work? And I'll explain it in a second. But basically, you get a nice hash map of your URL query parameters, and then you can do whatever you like with them, like that. And the question is, how the heck does this work? So the answer is plugins, which are basically a whole bunch of traits that allow you to implement kind of mix-ins on your... are they mix-ins? I don't know. It allows you to implement basically extensions to existing types, but using kind of dynamic typing under the hood. So you pass around a cache, which basically has all sorts of values in it. And as you want something, say from your request, you compute what you need using some sort of function, and then you store the value in the cache. So with the URL query parameter example, this thing is kind of like lazily evaluated. The first time you call it, it'll do some work out what the query parameters, rip them out, and then it'll store them in this hidden little cache on the request. And then the next time you ask for them, they'll be there straight away. So that's kind of the idea there. And the cache is a type map, which is where it gets fun. So a type map is a map from types to values, and it's implemented using the any trait, which basically says it's kind of like a way of examining your types at runtime. So using any, do you want to have a look at the definition? It's a compiler built in, but basically it allows you to do this thing where you get a type ID, and a type ID is essentially a unique integer that identifies that type. So how type map is implemented, if we want to map types to values, you can instead map type IDs to values, and then you just use a hash map of like integers to more any's. Actually, I think you have to store the values as dynamically typed as well and cast them out on the way. I think there's a bunch of unsafe casts in there that are actually safe though because of the traits that you've set up. So there's a trait that looks like this called key, where you say, okay, I want to use my type in a hash map, so I'm going to implement key and tell it what the value coming out should be. So in the case of our URL query thing, we say, it's actually just an empty struct, that type that we passed before. And we say that the value is this query map type, which is a hash map from strings to vectors of strings. So that's like, if you have a key, and then that key is set to multiple values in your URL query. And that allows you to put one of these in a type map. And then the next layer up is a plugin, which says, okay, something's a plugin if it implements key, and you also have to give an error type and a way to compute your thing the first time it's required. So there's a bunch of other traits in the background here as well, but the core of it, if you want to make a plugin, is that you implement this plugin trait for your thing. So for our URL encoded query, we give an error type for our things that could go wrong when you're parsing a URL. And then we also give a definition of this eval function, which basically just looks at a property of the URL on the request and then runs a function on that. And then we don't have to handle any of the caching ourselves, because the whole kind of plugin system will call this eval thing if there's nothing in the map and put whatever it returns in there for us. Yeah, and that's basically how it works. And if you want more details, you can see the plugin source, and my slides will be up online after this. So does anyone have any questions about that? Because it's a bit funky. When you read it, there's a bunch of traits and you're like, what's going on here? And there's one point where pluggable gets renamed to plugin, and then there's like two things that are called plugin, but one of them's like, hey, it's a bit weird. I think we should probably change that, but I haven't opened the pull request yet. Yeah, okay, so that's plugins. Now, so if we want to write a web framework in in Rust, you'd kind of want it to be fast, right? Because otherwise you'd just use Java or C or something insane, right? Or even Haskell. Yeah, okay, cold silence. So there's a web framework benchmark, which I'll just show you briefly. But I'm not sure exactly what their testing methodology is here, because they don't seem to describe it. But in this JSON serialization test, you can see the Rust source for this if you go and look this up yourself. It's pretty straightforward. It's basically what I showed before. But see that iron is down here somewhere. It does pretty well, but not that well. There we are. So we're the topmost Rust web framework, but we're beaten by a whole bunch of things, including this LWAN, which I looked up is a C microserver written from scratch to be insanely fast and uses like non-blocking I/O and all this great stuff. A few C++ things. Surprisingly for me, a bunch of like Java servlet container things, including, I think that's the standard servlet implementation. The Haskell thing, why? And then a few other things that I don't really know what these are. Yes?
How much of that might be the blocking I/O you're talking about?
I think probably quite a lot of it is the blocking I/O thing. And I was trying to look up how to improve this benchmark thing, because they do it with various numbers of threads and stuff. And the Rust implementation here, the iron one, is only very new. So I think I'd put down its relative slowness to it being an implementation that hasn't been really optimized or tweaked, possibly not even using the right number of threads. And yeah, obviously not having non-blocking I/O, which makes it a bit slower. But it still does better than loads of other things that you'd probably use to write web apps, including Go and Flask, which is like way, 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 way down. It's like, yeah, getting smashed. And probably most things written in Ruby as well would be down here. Yeah, yeah, there's a lot of things down here. But again, a lot of these probably haven't been optimized either. But they're on like less than 1% of the fastest thing, which is that crazy C thing. Okay, so that's kind of the performance story as far as I can tell. But it runs on embedded systems. It works pretty well for most things. As you can see, it's not like really slow. It's better than using Flask, and you get all the nice advantages, as I said before, of like cargo and packaging and that sort of thing. And yeah, that's basically it. If you'd like to help out, these are kind of the things that need doing. Obviously, improving performance and benchmarking would be good, because it's been the work of mostly one person over a year and a half or so, maybe 2 years now. And that's Jonathan Ream in San Francisco. And he's done loads of stuff for it. But having more people on board would be great. Integrating with more databases would be exciting. There's a new ORM for Rust called Diesel, which would be cool to integrate with Iron, make it easy to like connection pool and do that sort of stuff. HTML templating libraries and scaling Iron apps across a cluster, which is only something that I've gotten interested in recently, but I don't think it's going to be the next Erlang, but it could be good nonetheless. Yeah, and then if you wanna like really good intro to Iron, Brian Anderson has a whole walkthrough of him basically working out how to create an app in Iron, because he's a core Rust developer but had never used Iron before and wrote this thing of being like, oh my god, how does everything work? And I've also written a thing called Festivus that does basically everything you can do with Iron, like database interaction and routing and querying and all that sort of stuff. And it mostly works. So yeah, thank you very much for listening. That's Iron. Do we have time for questions? Or are there any questions?
We totally have time for questions.
We don't?
We do.
Oh, we do. Okay.
Questions were banned, right? First of all, a comment. Serde, I don't know how you pronounce it either. Serde, S-E-R-D-E.
Yeah.
Does work on stable. It
does
has
it?
some build.rs magic that auto-generates code at build time. You don't think about it.
Yeah, no, I don't count that as working on stable. Sorry, Eric.
Some of the auto magic, but you still get, you can still put attributes on the struct and still derive the thing, and then it automatically generates it for you. So it's almost invisible as a user of it.
Yeah. Okay. I was using...
The reason I use it is because I found the Rust C encodable, decodable stuff is good if you're defining your own JSON API, but it's not flexible enough if you want to implement someone else's JSON API.
Okay, like
so if you need to do things like have the JSON keys renamed to be something that has a dash in them or something that's not valid as a Rust identifier.
Yeah.
There's no bugs like keywords in Rust will fail to decode and encode.
Yeah, right. Keywords will fail to encode. Yeah, so if you have type is one I keep running into. If you have type : in your JSON API, you can't implement that naively.
That's true. Yeah.
Number one. Number two, if you were to, let's say you were to rewrite this in some async IO library.
Yeah.
You can't forbid blocking operations in Rust at declaration time.
No.
So it would be quite normal, I expect, to have a handler that might block.
Sure, yeah.
What would you like that to look like in an async?
I must admit that I'm not particularly knowledgeable about async stuff. Like I really haven't done that much or really anything at all. So I don't know.
Cool. Yeah.
Any other questions? Nope. Let's give another round of applause. Oh, sorry, one question.
Thank you.
So would you actually use this for doing a real project? Like, is it mature enough to be used for, like, not even necessarily a service, but like for an actual website rendering actual templates and doing something like that? Or
yeah, I think it's definitely ready for that sort of thing. Like it's very well tested. It's been stable for about a year now. The API is just like settled down like that. It's really just performance that we'd want to improve, but it's still good, right? Like it's still better than a lot of things. So yeah, I think it's pretty much ready. You can do SSL, I think, yeah.
Hyper is SSL built into it. It's a little bit broken, like cert verification doesn't work right, and there's a couple other bugs that are being
Hyper has SSL stuff built into it. It's a little bit broken. SSL verification doesn't work in some cases, depending on how things are verified. There's a bunch of bugs open on both Hyper and Servo to address that. Presumably, they'll be addressed at some point in the near future. But
yeah. Okay, cool.
All right, another round of applause, then a 5-minute break.
Thank you very much.